Can anyone check if the streaming is fine, as in the audio? And can someone speak as well? Glory Alex or Anshika or somebody else, can someone confirm whether the link that I sent you is working? Okay, I guess it is working.
Yes, it is working.
Yeah, sure. Thank you, Glory Alex. So, in the previous class, right, we were discussing about the process and threads. So, in the previous class means the class that we had on 18th May. Okay, afterwards we did not have class, and so in this particular thing, we were learning about processes and threads. Okay, and what we were interested in was we wanted to know how we can actually make use of threads. Okay, so are you able to see my screen? I hope not, right? Just a second. Yeah. Okay, are you guys able to see my screen? Students? Yeah, okay. So we were learning about the processes and threads. So a process means that whenever we have to run a code on a computer, so code means whatever computer program that we have written, it could be interpreted or it could be compiled. Okay, so if it is compiled, it means that we have the source code of the program. Let's say a C program, we have written hello world program. So what we do is we will compile the program, the .c file or the .cpp file with GCC or G++, and we will have the executable file. Okay, now we will load the executable file into the memory, and that file is what we execute as a process. Okay, so a process means that it will have the code, it will have the data, and it will also have the files, and it may be using the memory locations in the registers or in the stack, etc. Okay, and a thread is one what do you call as a thread? As a single segment of a process. Okay, so a process will contain a thread and the code, data, files, registers, and the stack. So the threads can be single threaded or it can be multi-threaded. Okay, so process means any program that is in execution, and thread means a segment of a process. So as you can see in this image, this is the image of a process that is given. Okay, and you can see that it also contains a thread. So you need to understand that a thread is a segment of a process. Okay, and you should understand that a process is loaded onto the memory by the operating system. Okay, and it is run and it is controlled by the operating system. While when I say about thread at present, thread means that I am going to spawn segments in my process. So what you see over here is a curly line over here, right? It's a curly line over here, and this is representing one single thread. Okay, when I say that a process can have 5 threads, you should understand that it can be, you should visualize it like it has 5 such curly threads. Okay, 5 such curly lines. And that is the reason why it is saying that, so in this particular table, we are differentiating between the process and the thread. So the process is on the left column and the thread is on the right column, and it says that the process takes more time to terminate and the thread takes less time to terminate. Okay, because a thread is controlled by the code inside your process. Then it takes more time for the creation of a process and it takes less time for the creation of a thread. It also takes more time for context switching in terms of a process, and it takes less time for a context switching in terms of a thread. Okay, so let's go forward. Let's try to understand a bit more of processes and threads. So this is the link that I had sent you in the previous class at the end. Students, just give me a minute. Hello. Okay, WhatsApp అనిపించా. Okay. So I told you there are different types of threads. Okay, so there are mainly 2 types of threads, which are user level threads and kernel level threads. So we are interested in the user level threads, and now let me just see what more I can tell you in the threads. Okay, so we have learned about recursion, right? So the reason why I am telling you about recursion here is, when we learned about recursion is when a particular function calls itself. Say for example, Fibonacci or factorial, right? Those are the programs which we have written using recursive functions. So a recursive function means that every time the function calls itself, at a point in time t when the function calls itself, there is a particular context from which the function is calling that and the same function again, meaning that there are a set of values on which this particular function is operating at present. Okay, so if I am saying about factorial, it could be n into n minus 1 factorial, that is what it has to return. So n could be 100 at this stage, and so it could be 100 into 99 factorial. Okay, so that value 100 and 99, those are actually the state of the program at that particular point in time t1. Okay, so this particular state of the program is pushed onto a stack, and this stack is used whenever the program returns to the calling function. So at t1 time, function factorial was called, okay, with let us say context c1, and then at t2 time the function factorial was again called with the context c2, then t3 with another context c3, etc. Okay. So when it is actually returning back to the calling function, okay, it has to get the values on which the function factorial was earlier operating on, and this is available in the stack. So when I say about the recursive stack, I will just show you what I mean, recursive stack. Right. So which means that, you know, whenever a particular function is called, it is added on top of the stack. Okay, the context is added on top of the stack, and when you are returning back, so at the fourth call, fact of 1 is equal to 1 is added, and when you are returning back, it is the second last one that it has to pick. So which means that it has finished executing for fact 1 is equal to 1, and then it has to return back to the next one. So 2 into fact of 1. Okay, so that is the context that we had already pushed onto the stack, and once it returns, it takes the you know, previous thing that we had pushed onto the stack, etc. So same way, so that was about the stack space. Okay, that was about the stack space. So same way in a thread as well, each thread has the different states. It has the program counter, it has the register set, and it has the stack space. Now what does the program counter in a computer program do? A program counter means that it is pointing to, program counter is a specific location in the computer memory which is pointing to the next statement that your computer program has to execute. So let us assume that your computer program is at the statement number 11 right now. So the program counter will have the value 12, which means that after finishing execution of line number 11, it has to move on and execute line number 12. So that is the program counter. So in the, when the program counter is actually looked into, it will have the address of the line number 12, which is there in the computer memory. Then it will have a register set, then it will have a stack space. So just like how I told you about the recursive stack, now you have two more things like the program counter and the register set. So there are some similarity between threads and processes. Only one thread or process is active at a time, okay, and threads are not independent of each other, and they share the code, data, OS resources, etc. Okay. So we have seen earlier when okay, let me show you that. So I had started discussing about the processes and threads and multi-threading from the context of running a program on our computer, right? So let me just wait until the system monitor opens up. Yeah, I think the system monitor must have opened up now, but yeah, it has opened up here. Yeah, so you can see that this is the system monitor of the genome of the computer that I am using right now, okay, and you can see that it shows the details of 8 processors: CPU 1, CPU 2, CPU 3, CPU 4, 5, 6, 7, 8, okay, and you can see that almost all of it is being utilized at around 50%. And you can see the RAM usage, it says that around 6.7 gigabytes of 7.6 gigabytes has been used. And if you look at the processes, which we had already looked at earlier, right? We had tried to run the factorial program, we had tried to run the hello world program, and we have seen that we can also kill that process by taking the process ID, right? By taking the process ID of a particular process, we will be able to okay, so this ID that you see over here in the fourth column is the process ID of the processes that you see on the left side. So if you use this process ID, you can kill the process that you can see on the left side. Okay. So only one thread or a process is active at a time, and within the process both execute sequentially. Okay. So if you look at the similarity between a process and a thread, a process can be thought of a single person doing all the work, okay, and a thread can if you look at the similarity of a thread with respect to a single threaded process or a single process, it means that there will be again one single thread of execution, okay. And both the threads and both the processes can create children, meaning that it can fork the code, meaning that at particular point, if my program, or it should be thought of this way, given a problem, as a programmer I can decide at which point in the program has to split into two processes or two threads or into multiple threads, and these multiple mathematical operations will all be done independently now by the different threads, okay. So between the processes and the threads, a thread is not an independent entity, while a process is an independent entity, and threads are designed to assist each other, and processes may or may not do it, okay. And then we have looked at something called the user level thread and the kernel level thread, okay. So user level thread is what the user has control over, and the kernel level thread is something which the operating system controls with. That is what you should understand at present. Now to explain how this multi-threading really works, let us take a look at a problem called dining philosopher's problem, okay. So I searched for dining philosopher's problem, and you can see that the first link that I got as the search result is from the tutorials point, and it says about the dining philosopher's problem, and the second link is from Geeks for Geeks, which says dining philosopher problem using semaphores. So let us take a look at the dining philosopher's problem from the first link, okay. Let us try to understand what exactly is the dining philosopher's problem. Students, are you with me? So we are discussing about multi-threading, okay, and before we can do it with Python programming language, I want you to get motivated with what exactly is multi-threading, okay. So multi-threading, we can think of it this way. How many of you play cricket, or how many of you have played cricket any time in your life? 21 students, okay. Prince Glory Alex says that he has played cricket. Praveen says he has played cricket. Shubham Joshi says he has played cricket. Rohit Raj says he has played cricket. Afrit says he has played cricket. Galangi Charan says he has played cricket. Karthikeyan says he has played cricket. Prajwal Venkatesh says he has played cricket. Narappa Reddy Jayesh says he has also played cricket. How many of you played football? Okay, and few more hands have been raised, and we know that there are multiple games. So cricket, football. Cricket and football are two games where you have more than one team member per team. Okay, and at the same time multiple team members will be playing. Okay, and at the end the team which played well coordinated and which scored the most points will win. Okay, so that is what happens in the game of cricket and in the game of football. While in the game of chess, okay, while if I ask you if you have played the game of chess, chess has only one player, okay, and an opponent. So chess is played between two players and or two teams, and each team can have only one person. Only one person is needed there. So which means that whatever computation and whatever movements is done by that single person. Okay, so one single person will be playing in the interest of one side in a chess game. Okay, say either a black coins or the white coins, white chessmen and the black chessmen. So you choose either one color, and then you try to win that side or win that color. And what you will do is, one single person will be sitting down, will be carefully looking at what the opponent is doing, and will carefully calculate the next moves, and will do the moves, and will finally win the game. So that is how a chess game works. Is that how a cricket game or a football game works? So let's assume football game, that will be easier. So we have how many people? 7 people or 11 people? So we have more than 2 people in one team, and we may have 7 or 11 people depending on the kind of football that we are playing. And what happens here is, it is not just one single person who is going to control the ball movements. Okay, it is all the people in the field who is going to compete for the ball. So the people in the same team will try to play a coordinated game, where they will pass the ball strategically among the players, such that they will be able to get a goal. Okay, and this way you will try to obtain maximum points in the football game for your team, and finally the team which scores the maximum points will win the football team. Okay, so why did I mention about the chess game and the football game? So the chess game can be thought of as a single threaded process, and the football game can be thought of as a multi-threaded process. Okay, where what I am trying to tell you now is, let us say that we have a football team with Ayan Guru Ishwar, Afrit, Aluri Sanjana Rao, Anshika, Bhubesh Gupta, Galangi Charan, and Harshit Kumar, and Prince Glory Alex. Okay, so these many students whom I have seen in the name list from the first till Jaladi Prince Glory Alex. Okay, now this is one team who is playing the football game. Now this team can be constituted as a process in a computer program. This team can be constituted or thought of as a single process, and each member of this team, that is Ayan Guru Ishwar, Afrit, Aluri Sanjana Rao, Anshika, Bhupesh, Galanki Charan, Harshit Kumar and Jaladi Prince Glory Alex. Right? All these people will act as individual threads, okay, in the process. Now that is what makes it as a multi-threaded program, meaning that all these individual players will be acting as threads in a single process. In the single process, as we have already seen, right? Let me show you that. Not here. Yeah. Just trying to reload the image. Yeah. Okay. So each of the player in this particular football team that I mentioned, each player will be one thread, okay, and the team will be one process. Okay, so the team will be one process which has one code, some data, files, registers and stack, okay, for the threads to communicate each other with. So let's assume that there are two threads, Glory LX and Ayan Guru Ishwar. Okay, how do they decide when should they pass the ball, or whether they should pass the ball to the to Glory LX or Ayan? How do they decide? So that will be based on the code and the data and the files and the computation each of the threads will be performing. Okay, so that is what you should crudely understand what a process and a thread is. Now let us go and understand what is this dining philosopher's problem. So this dining philosopher's problem, I'm going to just read it. Okay, the dining philosopher's problem states that there are 5 philosophers sharing a circular table. So they are all seated around a circular table. They eat and think alternatively. Okay, there's a bowl of rice for each of the philosophers and 5 chopsticks. So each philosopher is given a bowl of the rice. But there is a problem. For the 5 philosophers, there are only 5 chopsticks. Okay, and each philosopher requires 2 chopsticks to eat the rice. Without the chopsticks, the philosopher doesn't eat. Okay, so a philosopher needs both their right and left chopstick to eat. A hungry philosopher may only eat if there are both chopsticks available. Otherwise, a philosopher puts down their chopstick and begin thinking again. Okay, so the dining philosopher is a classic synchronization problem, as it demonstrates a large class of concurrency control problems. Now, when I was discussing with you about the football game with all the different people working as threads in the program, okay, I'm not sure whether all of you would have tried to think how this computer program will work. Just a second, guys. Hello. Yes. Dell சொல்லுங்க. இன்னைக்கு வரலாம். நீங்கள் ஃபாத்திமா நகர் பஸ் ஸ்டாப் இறங்கணும். நீங்கள் IIIT திருச்சிராப்பள்ளி வரணும். IIIT திருச்சிராப்பள்ளி, இந்தியன் இன்ஸ்டிடியூட் ஆஃப் இன்ஃபர்மேஷன் டெக்னாலஜி திருச்சிராப்பள்ளி. ஆக்சுவலி நான் வந்து பஸ்ஸில் வரவே இல்லை இங்கே, அதனால எனக்கு எக்ஸாக்டாக தெரியாது. நான் வந்து ஒரு நீங்கள் இப்போ எங்கே நிற்கிறேன்? தில்லை நகரில். நான் உங்களை ஒரு 10 மினிட்ஸில் அப்டேட் பண்ணுறேன் எந்த பஸ் ஸ்டாப்பில் எக்ஸாக்டாக இறங்கணும்னு. லாஸ்ட் ஸ்டாப் தான் வரும் மோஸ்ட் ப்ராபப்ளி. ஐ மீன் லாஸ்ட் ஸ்டாப் இல்லை, விராலிமலை பஸ் ஸ்டாப்பில் வந்தேன்னா பஸ்ஸில் வந்தேன்னா ஃபாத்திமா நகர் தான் இறங்கணும். நான் கன்ஃபார்ம் பண்ணுறேன். ஓகே, ஷூர், தேங்க்யூ. அது ஃபுல்லாக உடஞ்சிருக்கு. ஷூர், தேங்க்யூ. Sorry guys, so I met with a small accident and my laptop broke into pieces, but unfortunately it's in accidental cover, so they are trying to come and fix it for me. Okay, anyway, so we are trying to learn about the dining philosophers problem. Now the dining philosophers, we have seen 5 philosophers who will be eating, and once they are not hungry anymore, they will go back, sit on the same chair and start thinking. Okay, the problem with this particular setting is that for the 5 philosophers, each of them has a rice bowl given to them, but each of them has only one chopstick to them. Or you can think that for the 5 philosophers together, they have total of 5 chopsticks, and each philosopher must get hold of 2 chopsticks for them to eat the rice. And once they get hold of 2 chopsticks, they will be able to eat. If they are not able to get hold of 2 chopsticks, then the philosopher will ideally have to keep down the chopstick that he or she is holding, and we should go back to thinking. Okay, so the dining philosopher is a classic synchronization problem, as it demonstrates a large class of concurrency control problems. Okay, now I was asking this question before I got the call. So I was saying, when I was discussing about the football game with the number of people working as different threads in the program, right? I'm not sure whether all of you must have thought about how you would program this particular game. Okay, which means that what kind of data would I pass between these threads or between these people, so that they will be able to understand the position, okay, of each player, and they should be able to then make a decision to which player I should pass the ball, or should I keep the ball with me. I may also have to read the position of my opponent team members, so which means that I should be able to read the position of the threats of the opponent team. Okay, and based on all this information that I gather, I should be able to play the synchronized football game, and that will allow me to win the game, right? So this is the level of complexity, or this is the kind of work that we may need to do in order to play a simple football game, if we have to program it by the if we have to program it so that the computer can play it. Okay, so here in this example, what we have is a dining philosophers problem. So dining philosophers, first problem. So I'm just searching again so that I can show you the image. Okay, so this is the dining philosophers problem, where you have 5 philosophers who are seated around a round table. Okay, and each of them have, okay, in this particular picture it is a fork that is shown, but you should understand that it's a chopstick. Okay, so they have plates, noodles, and the chopsticks. Okay, let's try to see the dining philosophers problem on Wikipedia. Okay, so this one is also about the same problem, where you have where you have five philosophers seated around a table, and the five philosophers have to eat. I think I saw a video here. Let me see whether I can play the video.
Problem is an exam problem to demonstrate concurrent algorithm design. A group of philosophers sits at a table.
Are you guys able to hear the audio from this video when I played? Oh, okay. So what I will do is I will just send you the link of from Wikipedia. Okay, yeah. So that is the idea is we have. So then there are other problems also, like the producer consumers problem, cigarette smokers problem, readers writers problem, sleeping barber problem. Okay, so we'll just learn about this dining philosophers problem over here. Okay, so the problem, as we can describe, it's about five philosophers seated around a table, and five of them having a total of five chopsticks, and they need to get two chopsticks in order for them to eat. Okay, so the dining philosophers problem can be thought about as like this. So this is for a particular thread. Okay, this is not for the entire program. So the entire program will be consist of five threads denoting the five philosophers, and then the shared resource of chopstick. So the chopstick is a shared resource between the threads, which means that once the philosopher 1 takes one thread, one chopstick, no other philosopher can take that chopstick, because the philosopher 1 has the chopstick. And how do you denote this? So you have to denote this on the using some mechanism, maybe by using a true or false flag or something like that. Okay, so here this is the pseudocode for a particular philosopher, and it says that what the philosopher does is he will acquire the lock for the chopstick 1. Okay, and he will acquire the lock for the second chopstick as well. Okay, so chopstick I and chopstick I plus 1 percentage 5, those are the two chopsticks that the philosopher has gotten hold of. So once the philosopher has been given these two chopsticks, the philosopher can eat the rice. So that is the part of the algorithm where the philosopher will be eating the rice. Now once the philosopher has finished eating the rice, the philosopher can keep the chopstick down and may go back to thinking. So what the philosopher will now do is will signal the chopstick I and chopstick I plus 1 percentage I. So now these two chopsticks have been kept down, and then the philosopher will go back to thinking again. Okay, so in the above structure, first weight operation is performed on chopstick I and then the chopstick I plus 1 percentage 5, which this means that the philosopher I has picked up the chopstick on his sides. Then the eating function is performed. After that, the signal operation is performed on chopstick I and I plus 1 percentage 5. This means that the philosopher I has eaten and put down the chopsticks on his sides. Then the philosopher go back to thinking. Okay, so difficulty with the solution. The above solution makes sure that no two neighboring philosophers can eat at the same time, but this solution can lead to deadlock. This means that if all the philosophers pick their left chopstick simultaneously, then none of them can eat and the deadlock occurs. Some of the ways to avoid the deadlock are as follows. There should be at most 4 philosophers on the table. An even philosopher should pick the right chopstick and then the left chopstick, while an odd philosopher should pick the left chopstick and then the right chopstick. The philosopher should only be allowed to pick their chopstick if both are available at the same time. Okay. So, what did you understand from this particular problem? So, this particular problem is kind of telling you that for a particular problem to be solved, we may have to have multiple threads working in synchronization between each other. Okay. If the threads are all going to access the resources at the same time, when there is a constraint on the number of resources, then it could lead to a problem where the threads will not get the needed resources and will keep waiting indefinitely for another thread to release the resource, so that this thread may be able to use that resource. But the other thread also could be waiting like that. So, and all the threads could be waiting like that for the resources to be freed by another thread, so that this thread may be able to use it, and this could lead to a problem called deadlock. Okay. And in this dynamic philosopher's problem itself, the difficulty with the solution is the deadlock problem, and they are discussing some ways to avoid the deadlock by giving some algorithmic tweaks to the particular problem. Correct? So, this is what you call as a dynamic philosopher's problem, or this is what you call as concurrency control problem in a multi-threaded program. Okay. Now, let me quickly ask you a very simple question. Let us assume you want to calculate the sum of two matrices. Okay. Let us assume that you have an n cross m matrix and another n cross m matrix, and you need to perform the addition of these two matrices. If a single threaded program is going to solve this problem, then it will have to do the additions one after the other. Okay. It will have to do the additions one after the other, meaning that it will have to do the addition for the row 1 column 1 both elements together, keep the result, then the row 1 column 2 for A and B together has to be added, and then the result has to be kept, and so on. While if I say that you can make use of multi-threading, then for the n by m matrix, you can do the computation simultaneously. So, if you have, let us say 20 threads, you can do the summation of 20 elements all together all at once, but this may not be possible if the summation requires the result from a previous stage. Okay. So, there you may have to do some better tweaks. So, this is the fundamental of how you can perform parallel computation. Okay. So, students, it is very important that I get some feedback from you regarding whether you understood multi-threading. Okay. So, now let us search for multi-threading in Python. So, I want you to go through this. Okay. And look at how you can do multi-threading. Okay. So, I try to explain what multi-threading is. Okay, so in computing, a process is an instance of a computer program that is being executed. Any process has three components: an executable program, associated data, and the execution context of the program. Okay, so that is the state of the process, variables, workspace, buffers, and the program itself. A thread is an entity within a process that can be scheduled for execution. Also, it is the smallest unit of processing that can be performed in an operating system. In simple words, a thread is a sequence of such instructions within a program that can be executed independently of other code. For simplicity, you can assume that a thread is simply subset of a process. Okay, so a thread contains all the information in a thread control block. So just like how you have the PID, the process identifier, you have a thread identifier, okay, a stack pointer, program counter, etc. for each thread control block as well. Okay, and you can understand the basic difference between a single threaded process and a multi-threaded process by looking at these images. So a single threaded process is similar to a simple process where you have only one thread in that simple process. Okay, you have the code, data, files, register, and the stack, and the thread. While in a multi-threaded process, the code, data, and the files are shared, while the register and the stack are there for each of the thread separately. Okay, so you can actually execute a thread in a process for some time, then stop it for some period of time over here. Okay, and then resume its execution. And thread 2 over here in this example has been executing continuously for a specific period of time, while thread 1 executed for some period, stopped for some period, and then executed for some other period of time. Okay, so here we have example for threading with print cube and print a square, okay, for a number. So you will start a thread with the target function that it needs to execute, okay, and the thread is started, and once the thread has finished executing, you have to wait for that thread to join back with the parent process, and once both the processes join, you are done and you will execute, you will stop. So this is how two threads have been created in this particular example. So what you need to understand here is, here you have two functions, print cube and print square. Okay, two functions are mapped into two threads called T1 and T2. T1 and T2 are started, and T1 and T2 are joined, and then you print done, and this is done by the done both after both the threads have completely executed. So I'm going to send you this link as well. So I want you to take a look at these things, and also try to solve the dining philosopher's problem. Okay, so before that I will take the attendance. Students, can you please tell me whether okay. Attendance students, Ayan Guru Ishwar,
That's it.
Abhishek, Aditya, Afrit,
Present.
Afrit present, Aditya, Abhishek, Akash, Aluri, Sanjana Rao, Anshika.
He was present, but you did.
Who was present?
Akash was present.
Akash. Yeah, Akash Yadav. Yeah, I have marked him present. Are you guys are able to see my screen, right? So P will be on the left side and absentees will be on the right side. So Abhishek and Aditya, then Bhadraksh Bhargava, Bhubesh, Galanki Charan, Harshit, Ruturaj, 13. Yeah. Fifteen. 19.
So 26 present.
29.
The 30 was also present.
31. Okay, I'll go through it once again. Abhishek, Aditya, Bhadraksh Bhargava, Bhubesh Gupta, Harsh. Bhubesh is present. Okay. 33 is present. I think 33. Yeah. Sure. So Bhubesh. Harshit, Ridhiraj, 11. Okay, sure. Thank you. Rituraj, Dheeras, Abhishek, Swaroop, Nishant Raj, Amulya, Nikhil Ubadhyay, Pankaj Trivedi, Raj Singh Vadodria, Rohit S. Belur, Sheikh Bashir Ahmad, Veera Subramanya Vignesh Vemula, Vishesh Nagar, Yama Venkata, Harish Reddy, Yelaganda Bhargavi. So these students are absent. Is that correct? Let me check if anybody has. Okay, 31 and 33 is present. 31 and 33 present marked. Okay, students, if anybody is present and I have not marked them present, please do let me know. Okay, sure. Thank you, everyone. So please do practice the multi-threading idea. Okay, and there is multi-threading in Python set 2 link also that is given in the Geeks for Geeks here. So multi-threading Python set 1, that is what you need to go
Roll
through.
number 6 present.
6, sure. 6 I have marked. Okay, thank you, everyone. Thank you.